my name is Carolyn Seepersad. I'm the faculty director of the new Center for Additive Manufacturing and Design Innovation. We're very excited to offer you a virtual tour of our space today. Our primary mission is to perform fundamental research that accelerates the adoption of additive manufacturing worldwide through innovative materials processing, process innovation, controls, and design. Come on in, let's take a look. So our Additive Manufacturing Center includes 8 founding faculty members who have a number of research test beds scattered throughout campus, ranging from very innovative micro laser sintering of metals to reactive extrusion of polymers to flash sintering of ceramics and a number of things in between. The core of the center, the new part of the center though, is here on the ground floor of ETC, which is our mechanical engineering building on the University of Texas at Austin campus. We have more than 3,000 square feet of space. It's separated into separate rooms for metals powder bed fusion, or DMLS, for polymer powder bed fusion, or SLS, and for liquid photopolymers, including stereolithography and digital anatomy printing. We also have separate facilities for metrology as well. So at this point, I'd like to introduce you to our operations manager, Dr. Jared Allison, who will take you into further detail on each of these rooms.
Hello, my name is Jared Allison, and today I'm going to walk you through some of the new capabilities we have at the Additive Manufacturing Center, starting with our EOS M280 direct metal laser sintering machine. Using this system, we can fabricate nearly fully dense metal parts with complex internal and external geometries. We're currently processing 316 stainless steel, but we can also process other metals in the future, such as titanium alloys, Inconel, and aluminum alloys as well. With this machine, we can make custom one-off parts, like this custom designed gear, and also complex lattice structures with a high performance that couldn't be fabricated using any other method. This process takes metal powders and fuses them together using a laser. Thin layers of the metal powder are spread across the build surface, and a 400-watt laser scans the cross-section of the part to melt the powders to the previous layer. This allows complex parts to be made directly without the need to melt off any binders as some other methods require. The build envelope is about 10 by 10 by 12 inches, so parts within those dimensions are well within the range of what we can fabricate here at UT. After the parts have been built and extracted from the machine, there's a variety of post-processing techniques we have at the center to create our finished parts. We have a furnace for heat treating and stress relieving the parts after the build, and since the parts are essentially welded to the build plate, we can cut them off using our bandsaw. We can also treat the surfaces of the parts using several methods in the form of grinders and sanders, abrasive bead blasting, and a vibratory polisher to improve the surface quality of fabricated parts. Any other machining efforts required can be done at the full-service machine shop right across the hallway. There are numerous applications for this technology in the biomed, energy, and aerospace sectors, and we're very excited to have this capability at UT to support those industries and more. Next, I'd like to show you our 3D Systems SLA 5000 stereolithography machine, which is part of the liquid polymer lab at the center. This system uses UV curable liquid polymer resins such as epoxies and acrylates to fabricate parts with tight tolerances in smooth surface finishes. This machine in particular has an impressive 20 by 20 by 23 inch build volume, offering a lot of flexibility in the types of parts that can be made. We're still in the process of getting this machine set up at the center, but we've already begun making small test parts using a transparent resin. The build process starts by filling a vat with liquid resin and submerging the build plate to evenly coat it into a fine layer. Then, a UV laser scans the build surface according to the part geometry, and the build plate is once again submerged into the resin bath to recoat the surface. After the part is finished, it is lifted from the resin bath to drain out the excess. Then the part is cleaned with isopropyl alcohol and the support structures are removed. Finally, it's post-cured in a UV oven to achieve the final part quality. Potential applications for this technology include robotics, where surface finish and tolerances can be critical, to surgical planning, where the transparent resins can be used to visualize surgical routes. We're very excited to have SLA capabilities here at the center. Moving on, I'm very excited to show you our Stratasys J750 digital anatomy printer. While this machine uses similar materials to the SLA 5000, it processes them in a fundamentally different way to achieve unique capabilities. It all starts in the material cabinet that houses cartridges of liquid resin that have different colors and mechanical properties. The resin is then pumped into the print heads on the machine and deposited as tiny droplets, much like the inkjet printer you may have at your house. UV lamps on either side of the print heads cure the resin as it is jet onto the surface, allowing for high-resolution printing and layer thicknesses as low as 14 microns. After the build, the support structures are removed with a water jet and dissolved in a recirculating alkaline bath. The inkjet technology allows multiple materials to be mixed during printing to offer full color parts, as well as parts with graded mechanical properties, like this honeycomb that combines flexible and rigid portions. The digital anatomy printer can also use resins that are pre-formulated to mimic human bone and tissue, which can aid in surgical planning efforts and reduce the need for cadavers, like this heart model that has the look and mechanical properties of a real human heart. We can't wait to explore all of the functionality this machine provides. For those of you that didn't know, UT Austin is the birthplace of selective laser sintering, one of the most established processes for polymer powder bed fusion additive manufacturing. SLS was developed by Dr. Joe Beeman and Carl Deckard in the 80s, and this is our 3D Systems high-Q selective laser sintering machine. This process allows you to make functional, end-use parts with a high degree of complexity because support structures are not required. Parts can be nested within the build volume to maximize machine utilization. There are a variety of materials available, but nylon is one of the most common. I have a couple parts that were made on this machine to highlight its versatility. This part has a highly complex, nested internal geometric feature that would be difficult or impossible to fabricate any other way. I also have a functional part in the case of this snap-through spring element that can be used in energy absorption applications. This process works in a similar way to the metal laser sintering machine, where thin layers of polymer powder are spread across the build surface. Then a laser scans the part area to melt the powder and create the part geometry. After the parts have been removed from the build chamber, they are separated from the unfused surrounding powder known as the cake, and the excess powder can be cleaned off. SLS generally requires fewer post-processing steps than some of the other additive manufacturing methods, making it quite attractive for complex parts. Applications for SLS can include end-use part fabrication, small lot manufacturing, aircraft ductwork, prosthetics and orthotics, or any other area where geometric customization is desired. This rich history of selective laser sintering development continues today at UT with our experimental lamps machine that is fully instrumented to allow predictive process control for enhanced part quality.
So thank you, Jared, for that fantastic tour of some of our commercial equipment in our new Center for Additive Manufacturing and Design Innovation. We'd also like to invite you to explore all of our research highlight videos. These videos are intended to highlight many of the research test beds that we have across campus that we haven't been able to highlight in this video tour. So please take a look at all that fundamental basic research that's feeding into the future of additive manufacturing. We'd also like to mention that in addition to the machines you've seen in our tour today, we also have quite a bit of characterization equipment that's available. Our center includes a CMM machine, a universal tension and compression testing machine, and we have access to a wide variety of microscopy and other materials characterization capabilities across campus. And finally, we invite you to work with us. We hope that this center will just be the foundation for further research in additive manufacturing. And with your help, we'll be able to grow the widespread adoption of additive manufacturing throughout the country and throughout the world. So please get in touch with us and continue this journey with us.